Okay, good morning, everybody. We're going to go ahead and get started. I'd like to introduce Tyler Shields from Veracode. I've worked with Tyler now, I guess, off and on for the past 6 or 7 years across 3 different companies. He's done some really interesting research into anti-debugging techniques and has compiled several dozen of different techniques. So even if you do this stuff all the time, chances are you'll see something that you haven't seen before. So I'll hand it over to Tyler.
Thank you. All right. Suppose I better start the slideshow. Oh, that's backwards. There we go. All right, so as Chris mentioned, I did some research into anti-debugging techniques, and I'm actually releasing, and it's actually on our website right now, a white paper that has over 35 different anti-debugging techniques. So even if you do this stuff for a living full time, you probably will catch a technique or two you may not have seen in the wild, or you may want to implement into your code. But so for today's talk, I'm going to be discussing anti-debugging from the standpoint of a developer who has a desire to implement these techniques into their code. Anti-debugging is absolutely not a silver bullet. It's not going to ever stop a very dedicated reverse engineer or cracker or whatever you're trying to stop with your anti-debugging technique. But hopefully it'll raise the bar. Even if it's just a little bit, hopefully it'll make it a little bit harder for someone to get in and reverse engineer your code. The goal is not to stop everyone, it's to make it more difficult for novice and even some mid-level reverse engineers. So who am I? My name is Tyler Shields. I'm currently employed by Veracode. Veracode does on-demand application security scanning for binaries, for websites. We do manual application security assessments. So everything in the application space. In previous lives, I've worked for Symantec and At Stake, which I also heard about the At Stake drinking game that's been going on here. If you hear somebody say they worked for At Stake, you're supposed to drink, so everyone in this room needs to make sure they take a drink later. Incident response and forensics handler for the U.S. government. I worked for an extremely large U.S. government network doing incident response work in the past. What I wish I was infinitely rich, a personal trainer to hot Hollywood starlets, and an all-around rock star. I am none of the above, but I'm working toward them. So the agenda, what we're going to cover, we're going to have a brief discussion of the problem statement and the terms. Why? What is the problem with anti-debugging? Why isn't it used more frequently? Why isn't it out there a lot more? Why should I bother with anti-debugging if it's not going to be a foolproof effort? Standing on the shoulders of giants, I did not come up with these techniques. I'm simply presenting them in a way that you can understand them. As opposed to looking at assembly dumps, we're going to be able to look at C code, which is much easier to grok. Cases of anti-debugging methods or classes. I divided the anti-debugging methods, the 30-plus methods that I researched, into 6 different classes that breaks them down kind of by the method, the underlying method that they use. So we'll go over the 6 styles of anti-debug foo, and then we'll talk a little bit about some of the anti-debugging methods. We're not going to have enough time to cover all 30-something of them. I think I got about a dozen in the slide deck, but at the end there's a link to the paper that's going to come out with this that has all of them in it, so you can kind of get all the details. All right, so first let's do a quick statement of the problem and some definitions of terms. Anti-debugging methods are consistently presented as machine code or assembly language constructs, making knowledge transfer difficult and limiting widespread use of the techniques. That's a problem. To the people who do reverse engineering for a living, to the people who understand assembly through and through, inside, upside, really well, it's not that big a problem. To the rest of the world, who's not as familiar with dead listings and ASM code constructs, we prefer high-level code. Much closer to English, or at a minimum, a really nerdy version of English, right? C language is easier to read. So I'm presenting these anti-debugging techniques so the average developers can understand them and hopefully give them a little bit more exposure. All right, so let's do a quick experiment. I debated putting this in here because I was afraid it might backfire with this highly technical crowd, but we're going to do it anyways. So I'm going to count to 5 on the next slide. I want you to put your hand in the air when you know what the code does. Be honest now. Okay, I counted fast because I know a lot of you guys. Anybody know what that code did? All right, good. That's what I was hoping would happen. All right, how about now? I'm highlighting the important bits, and I'm counting slower. All right. Chris got it. Anybody else get it? Anybody else catch that one? All right. How about this one? All right. I'm not even to 3 yet, and I'm seeing hands pop up, right? This one's much easier to understand. For those of you who either chose not to put your hand up because you don't like me or didn't put your hand up because you didn't get it, don't worry. I'm going to go through this one as well. I mean, this is going to be one of the first ones we talk about later on. All right, so let's do a quick definition of terms. Some of these terms may seem trivial, but I want to make sure that we're all on the exact same page when we go through the actual discussion of some of these anti-debugging methods. It's just to avoid any confusion later. So debugger, debugging. Tools that connect to the process that allow a person control the debugger, or allow the person controlling the debugger to interrupt, inspect, modify, and otherwise control the process as it's running. Debugging is the act of using said debugger. Anti-debugging is any attempt to thwart the debugging of our process, implemented from within the process itself or from a sister process. I mean, there can be a number of different ways that we can execute anti-debugging. Anti-debugging detects minute differences when our process is or isn't running within a debugger or within a virtual environment. Depending on how loosely you want to define anti-debugging, we can also include potentially anti-dumping, which I'll get to on the next slide, or virtual machine detection. So dumping, what's dumping is dumping a running process from memory to disk and recreating the executable binary. This is typically used to bypass packing and encryption routines. The binary may be encrypted and packed on disk. When it's executed, it has to at some point be put into clear text, and then dumping is taking that, or by clear text I mean a normal readable binary. And then dumping is using a dumper to take that out of memory and recreate the binary on disk. Anti-dumping is the same thing as anti-debugging, except it's used to inhibit the dumping of a process from memory to disk. Then we got anti-debugging and anti-dumping. This is what most InfoSec researchers are interested in, which is bypassing anti-debugging and bypassing anti-dumping efforts. They want to figure out how to get around those things that I'm about to present you to stop to allow them to inspect the code deeper. We also have anti. You get the picture. It's an arms race, right? It never really ends. We come up with a method that's going to slow you down. You guys come up with a method that's going to get past it. We come up with a new method, et cetera. So it's really an arms race. The more people implement these techniques, the more people publish methods to bypass them. That's exactly why it's not a silver bullet, and you're not going to be able to protect your code 100% with any of these methods. Put enough of them in, make it hard enough, maybe people will go away from it, maybe the less skilled or less determined will go away from it. And that's the goal of using anti-debugging in the first place. We raise the bar. So why should we bother? Why should we do it if it's not foolproof? Why should we do it if it's going to, give us an extra 2% ability to protect our code? We must always expect successful reverse engineering of our code. We don't have to welcome the occurrence. We don't have to want it to happen, but we must expect it to happen. So we'll protect as best we can. We'll put some due diligence in. Laws can't possibly work. This is demonstrated by MP3s, music piracy. You can put all the laws you want on, DMCA and all those other laws about stopping reverse engineering and all that stuff. It's not going to work. It's just too high level. So let's actually implement something with a little bit more teeth to hopefully slow it down. Click-through EULAs are ignored, and soft methods of protection just aren't going to help. So the goal is to slow down subversion of our software registration or cracking. It probably won't be by much, but at least it'll help somewhat. And we'll add another layer to the security onion and raise the bar that next little notch, make it just a little bit harder. It's low cost. We should care because it's really low cost. It's short code segments, sometimes as short as literally one API call, and you've got an anti-debugging method. And it equals quick implementation. It's trivial to use the information in my paper and the code snippets that I'm making available to write a large anti-debugging library with 30-something different methods that you can just make a call to. Like I said, it's not going to be foolproof, but hopefully it'll make it a little bit harder. So I've used the term raise the bar. What does that mean? It means adding another layer of defense in addition to registration code, binary packing, obfuscation programs, stripping your debug symbols, all the different things that we already do when we create our code in binaries. Throw these little snippets in there and make it that little bit extra more difficult. If you're a malware analyst, I think you should care about this talk, right? Most of the malware analysts, most of the reverse engineers that do it for a living look at it from the assembly dump listing, and they may not have ever seen it in C code. They may not have ever seen what it looks like to the developer in the field. So the latest malware threats use AD pretty extensively to stop or slow down debugging and reverse engineering. So while a malware engineer might be familiar with many of these techniques already, understanding it from the viewpoint of a developer will allow them to identify other methods, other newer methods that we may not know about right now faster, because they'll know what it looks like at that higher level language. And you should care because it's another brain exercise. Exercise your brain. Anti-debugging is fun. It's cool. It's closer to being a rock star. Maybe not. Yeah, it won't help me with being a rock star, but it is fun in a nerdy sort of way. So the hardest part about this is going to be knowledge transfer, and hopefully we'll look into some of that today. So standing on the shoulders of giants, that's the first thing I wanted to put out there. I'm not going to read through this list. It's in my paper. These are the people that did a lot of the research, the technical legwork of coming up with these anti-debugging methods, and there's still more being created and done every day. And here's a second page of really smart people, some of which are actually here at this conference, so I wanted to make sure that they were thanked for the work that they've done in coming up with these methods. So, all right, let's break down some anti-debugging methods into different classes of anti-debug foo. This is just an actual artist rendering my mom picked up for me in high school, believe it or not, of debugging, which I actually broke the frame apart and took the thing out to scan it for this picture, but I just thought it was pretty cool, so I wanted to make sure we're going to stop anti-debugging here in our presentation. And again, if anybody has any questions, please throw up the hands and make this interactive if you want to talk about any of these as we go through them. All right, so here's our anti-debug classes. Excuse me, I broke it up into 6 groups. API, process and thread, hardware and register, exception, modified code, and timing-based. I'm going to discuss 5 of the 6 in the slide presentation. I'm going to skip over one of them primarily because it's a little bit more difficult to talk about, and it's probably better just left in the paper. It's about as close to a definition of classes as I believe we're probably going to get. There's certainly going to be some overlap. In some methods there might be a process and thread block direct write followed by an API call or vice versa. So there's going to be some overlap, but I tried to put each method into its own classification bucket as best I could. In general, the most obvious group was chosen, so we'll go through each of these on the next few slides. All right, so API-based detection. It's the most straightforward method of anti-debugging. It uses documented and undocumented APIs provided by the operating system to detect minute differences between when a process is and is not running underneath a debugger. Using internal API calls that access, usually PEB and TEB, which I'll get into, memory regions on your behalf, so you don't have to actually go in there and look at those values by hand. It can be as trivial as a call to is debugger present, which we saw. It can be more advanced, such as a self-debugging test where we fork a child that comes back and self-debugs, things like that. Process and thread-based detection is one level deeper. It's essentially looking at the process and thread blocks for our process that we're trying to stop debugging on and making choices based on information inside these memory blocks about our process and threads to determine if we're running underneath a debugger. APIs can be hooked and modified fairly straightforward, fairly easily, and this hopefully gets us around some of those API hook methods of anti-debugging or anti-debugging bypass. Direct access to the process and thread blocks holds pertinent information for us. So it holds things like the being debugged flag, debug port information, static strings, heap information. All of this stuff is tweaked slightly different when a process is set up and run underneath a debugger. So we can use direct process and thread analysis to detect these differences. All right. essentially, with the process and thread block detection, we can bypass API-based models and go direct. That's the gist of that. Hardware and register-based detection mechanisms is using registers and the CPU itself to detect the presence of a debugger. Directly accessing the processor components to check for things such as hardware breakpoints and other assorted registers, which I'll get into in a little bit. We no longer have to rely on software-based discrepancies to detect the bugger. We can look at the actual things on the hardware, registers on the chip, to detect if debugging is taking place. Exception-based debugging, it looks for differences in exception handling in the process depending on whether it's running under a debugger or not. Generally, and I'll get into in another slide, the process of exception handling and how it works, that's slightly tweaked and slightly different when a debugger's in place. So we can use exceptions to detect the presence of a debugger. Basically, our code triggers the exception, and based on how that's handled, we detect the existence of the debugger. So there's a number of different exception-based methods that we'll go through. Modified code is the one that I actually don't have an example in here for, so I'll get into that a little bit. It's essentially the process of making our process analyze itself from modifications. It's taking our process, making it self-aware, and making it know what its own function should look like in memory, and then scanning memory using either a CRC or a hash or something like that to determine if somebody's modified any of those functions, or thrown, for example, a software breakpoint into our function. We'll be able to detect that with modified code-based detections. This includes software breakpoints, which must overwrite an instruction with the 0xCC opcode. So that's modified code. Timing-based detections, probably the simplest conceptually to grasp. When a process is executing instructions, it executes very quickly. When, for example, we're single-stepping, it doesn't execute nearly as quickly, right? We have to step through each individual instruction. So if we make a timing call, and then we're single-stepping through a bunch of instructions, make another timing call, and calculate the delta between those timing calls. If it's above a threshold, an arbitrary threshold that we set, we can see that somebody's at least single-stepping our code. We can probably do that with that, and also detect things outside of single-stepping, but the variance and the accuracy of our delta has to be quite a bit more spot on for that. All right. So I'm about to get into actual methods here. Any questions at this point on the classifications or the high-level review of anti-debugging and what we're looking at this point? All right. We'll go through a bunch of examples then. Get right into it. All right, so quick technology background on API-based debugging. We're only going to be talking about x86 systems, first of all, and Microsoft Windows operating systems, 2000 XP Vista. We are not talking about any 64-bit debugging or anything of that nature at this point. Some of the methods are specific to certain debuggers. I'll try to mention that where it's appropriate. In the paper, it does specifically call out certain methods as only working on like Ali debug or WinDebug or whichever one it targets. So let's quickly go into breakpoints. A lot of anti-debugging methods involve detection, triggering, and other handling of breakpoints. Breakpoints are program locations we want to stop or pause a process, right? So the debugger will say we want to stop on this particular instruction or this particular function call and allow the debuggee, the person running the debugger, to actually get in there and analyze memory and analyze what certain variables are set to. Breakpoints are program locations where we want to stop the process. So this is done to read sections of memory, hardware registers, understand what the code does in more detail. Breakpoints can be triggered in two fashions, relying on the hardware to generate an interrupt, or inserting a specific breakpoint instruction into the process at the location we wish to break. Former is called hardware breakpoints, the latter is called a software breakpoint. Software breakpoints insert an interrupt 3 into the process in memory at the exact location where they want it to break. So the debugger saves the opcode that it's overwriting in the process at the point at which it wants to break, saves that off, and overwrites it with the 0xCC opcode, which is the software breakpoint opcode. It's a 1-byte opcode that triggers a software breakpoint. So when the process is running and it hits that trigger, the breakpoint exception is triggered, the debugger captures that exception and stops the process and allows the person to go through and analyze and modify the memory. When the debugger triggers the process to continue, it backs the instruction pointer up by 1, replaces the original opcode back where the 0xCC opcode landed, and says go ahead and run. And that's basically how a software breakpoint operates. Hardware breakpoints operate differently. They rely on debug registers within the hardware to hold a memory address, a status, context, and information about a spot that they want to break. Breakpoints are triggered when the target address is seen on the memory bus. The target address is stored within the debug registers, and when that is seen on the memory bus by the hardware fault, not an exception at this point, the hardware fault is thrown, and the debugger can catch it and stop. There's 8 debug registers. The first 4 hold the memory addresses we want to break on. Then there's a control register, which holds the type of access we want to break on, a read, a write, or an execute in that particular memory location. And then there's a status register, which is used to contain the status of which breakpoint was hit when it occurs, stuff like that. The other thing I want to talk about before we get into the actual details here is single stepping, which is using a debugger to execute a single instruction at a time. This is achieved by setting a flag within the processor called the trap flag. When that flag is set, execution of any instruction triggers a breakpoint every time. So every instruction occurs, a breakpoint gets triggered, so that way we can single step through the process. All right, so what are the pros and cons of API-based AD? Very easy to understand conceptually. It's 1-2 calls to some APIs that are either documented or undocumented by Microsoft. Generally understood, information is available about a lot of these methods. They're short, really short, generally. Bypassing is usually easy due to trivial complexity. That's a con, right? Due to how easy they are, they're easier conceptually to understand, but they're generally easier to bypass. And the downside is they're most frequently used, so a lot of the people who would be reversing your programs are going to understand how to bypass these fairly quickly. All right, so here's the first 2, find window and registry key. Registry key is a little bit different, but find window, for example, OllyDebug, when you run it, it has a default window class of OllyDebug, so we can use the find window API, scan all the process in memory, and look for ones that have a window class of OllyDebug. Pretty straightforward, right? We just iterate through all the processes in memory, detect using the find window method. We can actually detect which ones have OllyDebug. WinDebug, I forget what the full string is, but it's something about WinDebug something. And Visual Studio has a default string as well. So we can just use this call to iterate through all the processes and look for a window. Pretty straightforward. It's called WinDebug frame class. That's what WinDebug is going to be called. Registry detection is very basic check. It doesn't check that a debugger is running. It checks that it exists on the system. Probably use it in a more heuristic fashion as another point that might, help detect debuggers. But I probably wouldn't use that as a full break to break out of a process based on a debugger being present on the system. But essentially, you're checking registry keys. The first one there denotes which debugger is set up as default, the default debugger for when a program crashes. The other 2 are shell extensions, like the little drop-down menus, like debug with or whatever. So again, that one's more heuristic based, but it's a good way to know that at least a debugger is installed on the system. These 2 are probably the 2 most common ones that anybody who's done any reading or research into anti-debugging has seen already. The first one is basically a call to isDebugger_present, which is a provided API by Microsoft, which checks to see if a debugger is attached to the running process. The API call checks, what the API call does is it actually directly checks the process environment block, the PEB, for our process and looks for the being debugged flag. If the flag is non-zero, it says, yep, we got a debugger attached. So it's literally just a simple basic if call, if is debugger present, and then we pop a message box, debugger detected. Very easy. Check remote debugger present is very similar, except it takes 2 parameters. The first parameter is a handle to the target process we want to check if a debugger is on. In our example, we use a call, we actually stuff another call in there to get current process, so we're checking ourselves. And the second value is the return value is present. The word remote in this one, within check remote debugger present, does not require that the target process is running on a separate system. It does not even require that it's a separate process. As you can see, we can just point it to ourselves. This API call uses a call to NTDLL NTQuery information process with a process information class of process debug port, which I will get to later as a totally different check. Output debug string on 2K and XP. This one's kind of neat. The return error message is what's used to determine if a debugger is present. If a debugger is attached, output debug string does not modify the get last error message result. So what we do is we essentially use a call to set last error message to set it to anything but the value 2. Whatever we want. In this example, I set it to 666. Nice happy number. And then I execute an output debug string of foobar. If get last error equals our value that we arbitrarily set it to, the debugger is detected. If not, no debugger is detected. So it's pretty straightforward. If no debugger is attached, get last error will return a different value than what we set. And if debugger is set, our variable doesn't change at all. So pretty straightforward one there. And it's a little different. Okay, NT-query information process detection. So this is NT-query information process is technically one of the less documented or undocumented or calls within NTDLL.dll provided by Microsoft. There's no associated import library with it, which requires us to use runtime dynamic linking using load library and get proc address to actually get a pointer to this function inside of NTDLL to make that call. I don't think, yeah, I didn't include the get proc and load library address in the slide, but those actual code is in the code snippets that I'm releasing and in the paper as well, so you can see how to do runtime dynamic linking. Uses a handle to the currently running process. In this case, the -1 there, the -1 on NT-query information process. The -1 indicates our current process. We could also put in there a call to get current process. I just chose to use -1 to shorten it a little bit. And the parameter 2 there is the value for process information class, value of process debug port, which is 7. So what this call to NT-query information process does is it queries the process looking for the debug port. If the return value is 0, that means that no debugging port is available and the process is not being debugged. If the return value comes back with anything other than 0, that's the process debug port, which means it's being debugged. NT-set information thread. So instead of querying a process in this one, we're actually going to make a call to NT-set information thread, which modifies thread information through the API. Again, the second parameter here is what's important. Again, this is dynamically loaded with getProc and load library. But the second parameter to the NT-set information thread call here is what's important. The thread information class of 0x11, right there, detaches our current thread from any attached debugger. We just simple one call, bang, debuggers will get detached. Again, we use get current thread there to tell the call to set information thread that it's us that we want to target. All right, so self-debugging with debug active process. A process can determine if it's being debugged by attempting to debug itself. Creating a child process, which then attempts to debug its parent, is one method of knowing if we're currently being debugged in the first place. We can only hook one debugger at a time onto a process. So if the child is not able to attach to the parent as a debugger, it's a pretty strong indicator our process is being run under debugger. Basically, we use a get current process call to get ourselves, then we fork off a second process with create process. And that child process then attempts to make a call to debug active process with the PID of its parent. If it's successful, we get one value, and if it's not successful, we see the other value. So. All right, process debug flags. Again, this is more information that's stored within the process environment block. The anti-query information process call is used again here, as you'll see. We're querying information about our process with a second parameter of 31. 31 is the process debug flags enum. So this returns a D word indicating if the target process is being debugged. It returns the inverse of the process debug flags, and thus if a 0 is returned, our process is being debugged. When the process is started within a debugger, there's a number of flags that indicate how things need to be set up. For example, heap information, which we'll get into a little bit, is completely different when a process is running under debugger versus running outside of a debugger. It uses a debug heap setup. So we can actually look at flags such as process debug flags or heap flags to get that information. That's what that first one does. Process debug object handles the next one here. We use a call again to query information process. First parameter of -1 indicating ourselves. Second parameter of 0x1e. This one returns a handle to the current debug object for the target process. If the target is being detected, it'll return a debug object handle. If it's not, you don't get anything back. So we can use this to determine the debugging status of a target process and act accordingly. The next one here is specific to OllyDebug. This one's kind of neat. I believe it might be fixed in the 2.0 version of OllyDebug, which is currently in beta. But essentially, we make a call to output debug string with a bunch of %s's in it, and OllyDebug doesn't like to output that and crashes. So it's a nifty little bug within 1.1 version of OllyDebug, anyways, that we can use as an anti-debug check. We then handle any exception that is made if OllyDebug doesn't crash, or the target debugger might be like something else might throw the exception here. We can handle that exception with a call below it. All right, so that's all for APIs, right? Those were all pretty straightforward, single calls, pretty straightforward stuff. Any questions on API stuff? Okay. So I want to go through real quickly exception handling. Basically, exception handling. Exception handling based detection it uses debuggers trap the exceptions and make modifications to the process, and then return those exceptions back to the execution of the process for continued handling. If this isn't done properly, passing the exception back to the process for internal handling, this can be detected. So let's run down the exception types within the Windows operating system. I actually stole this graphic. I have it referenced later where it's from, but essentially Microsoft uses a chain of exception handlers. Some variances depend on operating system. Vista does it slightly differently than older versions. But in general, you start with a linked list of vectored exception handlers, which is just a linked list of structures that contain pointers to the function that you want to call in the event of an exception. If none of those trigger, then it moves on to the structured exception handling chain, which is, again, a linked list of pointers to exceptions to handlers based off the exception. If none of those trigger, it gets handed to the unhandled exception filter, which is kind of like a catch-all. If an unhandled exception filter isn't registered, the process will probably crash. So that's kind of the chain, the linked list of linked lists chain of exception handling. The debugger gets what's called a first chance exception before any of these are called. The debugger can make changes to the application and return, it can either return the exception information directly back to the process for handling, or and thus bypassing this entire chain, or it can let it go through the chain, make changes, let it go through the chain. So the debugger kind of gets a first shot at the exception information. Depending on how the debugger handles it, we can detect that the exceptions occurred or didn't occur. Or I'm sorry, that a debugger is present or not present. So that's the basics of exception handling. These ones are a little bit harder to grasp because of the fact that this is kind of a difficult chain of events that we have to remember occurs. But hopefully we'll be able to go through some of these. So what are the pros of exception-based anti-debugging? Slightly more complex, right? It's, if it's slightly more complex to us, it's going to be slightly more complex to somebody trying to bypass it, making it sometimes more difficult to bypass. The debugger may or may not know how to completely ignore that the exception even occurred and give it back to the process for handling. Some debuggers are better at that than others. Cons of exception-based anti-debugging, it's slightly more complex, right? So it may help us, but it's also going to hurt us a little bit in that we may not understand how to implement these as well. Typically a little bit longer in length as well. So let's see what we get here. All right, the debugging interface is accessed by int2d. Interrupt2d creates an exception record, code of status breakpoint, which is handled to the kernel debugger, and then eventually can make its way up to a ring 3 debugger to trigger an exception in our code. So the application, if the application handles the exception, we're not running under a debugger. If the exception is handled elsewhere and passed back to us as handled, then we know that somebody else handled it, and it's a debugger that did it. What's also cool about this one is that int2d can be used as obfuscation of code when in a debugger, because it's debugger dependent, but it may or may not execute the instruction directly following the int2d call that we make. From my experience, OllyDebug, when you do an int2d, will run until the next breakpoint. Visual Studio will skip an instruction and then breaks, and WinDebug will stop after int2d, even if we tell it to continue running. It'll stop anyways. So it's kind of a neat little way to obfuscate code too, right? You can cause it to skip over instructions when in a debugger. So that's int2d. But basically, if we're just going to look at the code here, we see a try and an except block. In the try block, we have to use direct assembly to push out the int2d. But basically, if we handle the exception internally to our code, that means no debugger was present, right? If somebody else handles that exception for us and doesn't properly hand it back to us in an unhandled manner, we know that somebody else intercepted that and handled that exception on our behalf, and it's probably a debugger. int3 and f1 are both they operate exactly like the int2d. int3, an exception gets thrown. If under debugger, the debugger handles the int3 call, and an application will never occur. Using this discrepancy, just like int2d, we can detect the presence of a debugger. The F1 call is actually kind of cool. It's an undocumented opcode within the Intel chipset, 0xF1, which is also called the ICE breakpoint. It causes a breakpoint to occur that triggers a single step exception. But again, it's exact same conceptually with regard to how it's handled in the code here. One final one on this slide is the 0xCC detection. So I actually squished 4 different methods kind of into one here because they use the same code construct. But 0xCC detection is triggering a software breakpoint. And again, if it's handled in the debugger, it's not handled in our code, and we can use that as a detection mechanism. All right, this one's cool. This is the kernel 32 close handle. It's a little different than the previous one you saw because it actually operates completely in reverse. Close handle call generates a status invalid handle exception if we give it an invalid handle. So in our example here, we use close handle 1, 2, 3, 4, 5, 6, 7, 8. That obviously that handle doesn't exist, and the exception is generated and trapped by the debugger and handled there. It's slightly different because a call to close handle only raises the exception if a debugger is attached to the process. So what you see there is we had to flip the handling mechanisms at the bottom. If a debugger is not attached, the call simply returns an error code and continues on. So we had to flip those two at the bottom based off of how to handle it. Single step detection trap flag, so we can use a single step mode to detect the presence of a debugger. Basically what we do here, again, we had to do this in assembly. There was no other real way to kind of do this from C code. But the assembly calls there, it's very basic. We use push SD, which saves the flag registers from the processor. Then we OR the pointer to the trap flag with 1, which essentially sets it to 1, turns on the trap flag, which tells our processor we're now in single step mode. And then we pop all the flags back into their original position. During that pop, it's a single step exception will occur. So we essentially can trigger the single step exception. If it's handled at the debugger level, then we can detect that if they don't hand back an unhandled exception back to us to process within our code. So as you can see there, again, we do it in a try block, then the accept block, and based off of whether it's given back to us unhandled or handled, we pop the appropriate message box. And what's cool is we actually do it in just the 3 assembly calls, because the one that we trigger the single step exception with actually turns off the trap flag, so we don't have to do it in another call. All right, this one's specific to OllyDebug. OllyDebug interprets page guard exception as a memory breakpoint. So what we can do is we can execute a page guarded page to trigger that exception. And again, then based off of how the debugger handles that and passes it back to us, we can detect the existence of a debugger. So what the code does is we alloc a memory segment. We then switch the virtual protect to a page guarded mode, and then we try to execute within that page guarded page, and that triggers the exception, which then can detect the presence of the debugger. Control-C vectored exception handling. This one's kind of cool too. This one's specific to console programs though. So the Control-C vectored exception handling one won't work on Windows-based processes. But essentially, the console program is being debugged. When it's being debugged, the Control-C command inside that process window throws an exception that can be trapped by a vectored exception handler. If it's not being debugged, no exception gets thrown. So only a signal handler gets thrown. So what we do in the code is we register a signal handler and we register an exception handler, a vectored exception handler, which goes first in that chain, okay? And essentially, we trigger a Control-C by executing the generate console control event. And depending on whether our signal handler is called or our exception handler is called, we know whether a debugger is hooked or not. It's not there, the actual pop-up boxes I cut off just because I want to get 2 on the slide, but that's in the paper as well. This does not work against Olly. It only works against Visual Studio. So that's another thing to keep in mind. The next one is using the compare exchange 8b with a lock prefix. It's just like the other exception ones we've done. We're generating an invalid instruction exception here. The lock prefix, when used with compare exchange 8b, it's considered an invalid lock and causes the debugger to catch an invalid instruction exception. And based off of whether that's handed back to us unhandled or not, we trigger the appropriate following code. One thing that's interesting actually in this one, this call will cease debugging. It doesn't just hand back, it actually stops the debugging. One thing to know here, oh actually, yeah, that's right, this one. We have to set an unhandled exception filter here because it doesn't, the debugger will not hand back, so we can't possibly use the previous methods of handling. So what we do is we set the unhandled exception filter on this one. We trigger the invalid lock, which stops the debugger if one's attached. It ceases debugging altogether. In our code, if a debugger doesn't exist, our unhandled exception filter catches it. That's right, this one's a little bit different. Essentially, the unhandled exception handler is able to gracefully continue code execution when executed outside of a debugger. All right, so that was the exception ones. Again, those are conceptually a little bit more difficult to understand because you have to understand exceptions, which is a little bit more difficult to understand in general. Any questions on those ones before we jump into the process and thread block ones? Cool, because I'm running low on time. Process and thread block technology background slide. Notice the ... at the bottom of both of these structures. These structures are huge. I couldn't even, I was going to do a slide for each one, and then I realized that the print would be so tiny that I just chopped them off. But so essentially the process environment block holds the user mode parameters associated with the current process and contains all pertinent information at a process level that the system and we would care about for our process. Includes things like the process base address, heap locations, memory pointers, global flag, isDebug flag, etc. I mean, it's big. The thread information block contains all the parameters associated at a thread level that we would be interested in. Thread ID, parent process ID, pointer to the PEB is located within the thread, error information, exception information. So these are structures that hold information about the process and thread that we can directly query to determine if our process or thread is running underneath the debugger. Pros and cons to these. On the pros side, we're going direct. We are avoiding APIs, less chance of hooking, and generally harder to bypass than API-based calls. On the con side, we use undocumented structures that can change at any time if Microsoft decides that they want to move the operating system in a different direction and modify what the PEB looks like. These methods are going to break, or could potentially break. Again, these use runtime dynamic linking to actually directly access the information. It might be a little bit harder to understand if you don't grasp what runtime dynamic linking is and how it works. So the first two here. The first one is isDebugger present direct PEB access. It's just like the isDebugger present call, except instead of actually calling a function, we're doing what the function does ourselves. But the basic gist of this one is we use a call to NT-query information process to grab a pointer to our PIB, which we then look at the PEB base address within, and now we have a structure to our PEB. So that's going to be a repeating thing. Whenever we need to gain access to the PEB structure, we make that call to query information process, look at the offset for the PEB base address, and then basically put that into the PEB structure so that we can have better access to it. But anyway, so then from there, we look at the being debugged flag, just like isDebugger present does, except we're just directly querying that from within the structure ourselves. The second one, I mentioned earlier, that under debugger, heap headers are created differently than normal. They have the heap header flag in particular will contain a different value when the process is started within a debugger and when it's not. So what this one does, excuse me, what this one does is we actually look at a heap, the read flags. Right, so we look at a heap header at offset 0x10, which has the heap header flags, will indicate if the heap has been created while in a debugger or not. If the heap was created under a debugger, the offset at 0x10 will be a non-zero value. So what we're doing here is we're looking at an offset of hex 18 from within the PEB, which is a pointer to the process heap, and then we're looking at an offset of hex 10 within the process heap, which contains flags about how that heap was created. So, and then if that heap was created, if that flag within the process heap has a non-zero value, we know that it was created from within a debugger. NT global flag, the PEB structure flags at offset 0x68 contain the start status of a process. So again, this also plays into the fact that the heaps are created different. So when we start up the process under debugger, this particular flag tells the process how to create the heaps, to create debug heaps instead of regular heaps. So again, we look at the offset of 0x68 within the PEB structure, which has the flag that tells the heaps how to be created, and that flag, if it equals hex 70, indicates that the heaps are supposed to be created in a debug heap fashion. The hex 70 comes from flag heap enable tail check, which is hex 10, flag heap enable free check, which is hex 20, and flag heap validate parameters, which is hex 40. You add those things together, and you get a flag of hex 70. So if that particular flag within the PEB structure is hex 70, we know that we're generating our heaps in a debug fashion, and thus a debugger is running. This one's Vista specific, and it's kind of cool. It's if when you create a process under Vista with no debugger, the main thread environment block for the main thread at offset 0x BFC will have a pointer. That pointer points to a Unicode string that references a system DLL. It'll have a pointer basically to like kernel32.dll or something like that. The string will directly follow the pointer, so the string will be located at 0xC00. If the process was started under a debugger, for whatever reason, I'm not entirely sure about this, why, but if the process was started underneath a debugger, that Unicode string will be the value hook switch hook enabled event. I'm not sure why they changed that, but so essentially what we can do is look at our thread, get our thread pointer, look at the particular offset, check it against, look at the particular offset of BFC, make sure it points directly after itself, which is just kind of a double check. You don't really need to do that, but points directly after itself, and then check that string. If that string in our code example here, we compare it against Hookster or something, I think I called it. Yeah, Hookster, which I set to a static value earlier in the code, but hook switch hook enabled event, if it equals that, it was started underneath the debugger. That's kind of a recent technique. I think it's only been discovered in the last 6-8 months or something, so I don't know that anybody's dug into the actual calls to understand why it puts that value there, but it does. So that's it for those ones. For the process and thread block, again, I'm only going through a sample of each of those, right? I've got a ton of those within the paper, but hop into hardware and register anti-debugging. So pros and cons. Again, it's another layer lower. We're directly looking at hardware here. We're bypassing even more of the operating system that would be able to detect or find us as in what we're doing here. They're harder yet to bypass and fairly easy to implement. On the con side, not a whole lot of research into this area, and there's a limited number of techniques available. As a matter of fact, I think I only talk about 2 of them. But so as I mentioned before, there's 2 different types of breakpoints, software and hardware. Essentially what we're checking for and finding with this AD technique is hardware breakpoints. When hardware breakpoints are set, the CPU debug registers will hold the specific breakpoint information. DR0 to 3 hold the address that is used to break the program, and DR7 holds the context information. So we can access these debug registers via a getThread context call. I mean, arguably this could be put under API debugging because we make a call to getThread context and look at the results, right? It's not, we're not directly accessing the hardware per se. But if any of those DR values is non-zero, that means the hardware breakpoint has been set. I mean, it's a very straightforward check. If any of those aren't equal to 0, we know that there's a debug or a breakpoint, hardware breakpoint has been set. This one actually, the guys that came up with this one are floating around the conference here, but hardware registration, I'm sorry, VMware, this one detects VMware by looking at the SLDT, or the LDT register. Basically what this one does is it makes a call, assembly call to SLDT, which is store what's in the LDT register on the chip. The LDT register will contain a pointer to a memory location that holds information that's pertinent to the operating system. So we can use this to detect VMware because we can only keep one chunk of data in memory, so VMware has to essentially emulate the LDT register, and it has to point to somewhere other than where the regular processor points to, right? Because otherwise you're going to have a collision there. So the regular processor points to a very static location, almost without fail, and VMware points to a very different static location without fail. So we can use that information, that discrepancy, to detect the existence of VMware underneath our process, and then if we want to dump out of it, we can. This was originally done with IDT and GDT, but due to the advent of multiple processors, it became a lot less accurate. And then so Val Smith and Danny Quist came up with this method, which uses the LDT instead of the IDT and GDT checks. And the last group, I'm right on time, the last group here is timing-based anti-debugging. They're super easy to implement. Conceptually, very easy to understand and can monitor large blocks of instructions if you want to keep a check on that, or individual instructions. On the downside, they're very easy to bypass and generally can be spotted a mile away. You just look for subsequent checks for time and then a comparison against the delta of those values. So from an anti-debugging perspective, they're easy to bypass. So we can detect single-stepping debugging by calculating the delta between two consecutive RDTSC calls. The call is returned in our code here to I and j. We do it consecutively. Then we take the delta of those two values, and just for an arbitrary value, I used hexFF. If the delta of those two values is longer than that amount of time, we're probably single-stepping. I mean, FF, that's pretty quick. I don't think anybody would be single-stepping and step through the code that fast. I mean, to the point where when I was doing this, when I was writing these, I literally was single-stepping like this, and it still caught it. So if the delta value is greater than FF, which is our arbitrary threshold, we're being single-stepped. NT-query performance counter, it's conceptually just like the RDTSC calls. We call it in succession, take the delta, compare it against FF. The other two methods down here, exact same thing. They're just different timing methods. One thing to note there is the getTime function, the getTickCount function is much lower precision. So your arbitrary value of hexFF won't work. You have to raise that up quite a bit. But all four of these operate in the exact same fashion, so I threw them onto one slide. That's a link to where the paper is right now. It's on Veracode's page. I also write on the 0 in a Bit blog, so I'll put a link on there and a story on there probably today or tomorrow at some point that'll have pointer to the paper and pointer to a fairly large, I think it's 90 meg or something, zip file that has all the source code, all the solution files for these, and actual compiled binaries for each of these examples. And actually, I'm going to see if I can even get this over there on the second monitor. And that's what the directory listing looks like for all the calls. So, I mean, there's a number of them that I didn't get a chance to talk to just for time constraints. But all of these are made available, all the source for it, all the binaries for it. So, again, it's at this URL. Any questions? I know I flew through that stuff, tried to get a lot in there. Yes?
So what kind of solutions do you suggest to developers who are trying to make their code bug-proof?
Implement as many of these as possible without causing yourself too much pain in doing so. Use binary packers, use a number of different things. You can't rely on any of them. And actually, you can't rely on any of them in concert to be foolproof. But if you put as many of them in there as you can, hopefully it'll become significantly harder. That's all.
I've seen some work done around core technologies, because when you know that this is going to happen, you try to take the worst case of the you try to defeat the break once, run everywhere attack, where I can crack your code and get it out and distribute it.
Yep.
And the way to deal with that, one way is to create these individualized black box distributions of your binaries. So that almost every person, or 1 out of every 100 downloads, is going to have a unique binary. That's something that
that's an interesting concept too.
some technologies have implemented. Microsoft's done that with some things. And it works.
Yeah, because it raises the bar again, so you have to break it every single time.
Yeah.
Yep, absolutely. Yeah.
What about defeating some like malware dynamic analysis stuff that doesn't actually debugger, like some detours that just rejects the user with DLL, something like that? What technique would you use for that?
As far as stopping someone who's looking at our code using detours or API hooking in user land to check it. That's interesting concepts. I mean, you could look at like the location. You could parse the IIT and look at the locations within the IIT, for example, and see where those might point to, and if they're within a specific range, that might work. You could also grok through like the first X number of bytes of each, follow the hop through the IIT to the target, which is how detours does it, right? And then it actually replaces, I think, the first 5 or 6 bytes of the target function with its own function and then hops back. So you can actually do signatures of those target functions and compare those to detect people using detours on your code. Absolutely, and some malware is doing that now. Yeah, I've seen that in the wild. So, yeah.
So, how do anti-debugging techniques tend to impact product maintenance?
That's an excellent question. You know, they're small, they're short. I can't imagine they would impact it too drastically, but I've never worked in a full-time development shop, so I don't know from the development side what kind of impact on maintenance that would actually have.
You get to debug your own stuff.
That's true.
Is that what you're asking?
That's true, but you could create.
A non-debug build, right?
Right.
You can do if that debugger on all this stuff.
Right.
I'm thinking that, but at the same time, sometimes run into timing issues. That if the anti-debugger stuff is running, that's going to change the timing of the program, which might be very consistent when the anti-debug stuff is running. As soon as you run a debug build, you don't have that, you can't reproduce the problem. So you really have to attach a debugger, so you have to go about the anti-debugging techniques.
Which I'm working on, by the way.
Sorry.
So which I'm working on, by the way. That's next speech. So, any other questions? Awesome. Well, thank you. Appreciate it.